This is Michael.
I'm Dennis.
I'm Ryan.
And I'm Thomas. And today you're going to learn the truth about neutron stars.
So to get down to the truth about neutron stars, we first need to start with when they were born. Now, neutron stars start as a mommy star, which is just a regular star with 8 solar masses. And a solar mass is just the mass of our sun. So these 8 solar masses cause an inward gravitational force that is balanced by an outward radiation pressure.
And this radiation pressure actually comes from a process from what is called nuclear fusion. And when nuclear fusion runs out of fuel,
then boop, the star no longer has any fuel in its core, and the only force acting on it is an inward gravitational force.
all right, and then this inward gravitational force creates an implosion from the star. And now all the protons and electrons that are in the star come together and collide, and they actually form neutrons. And now that's why the star is called neutron star, because 80% of the star is neutrons, and the diameter is only about 20 to 40 kilometers. Now these collisions that create neutrons actually form a huge amount of energy, and it creates a huge radiation blast outward from the star called a supernova. And this supernova will outshine any light in its galaxy. All right, let's consider the Bohr model for the hydrogen atom. So between the nucleus and the electron, you have mainly just empty massless space. And this gives the hydrogen atom a mass equal to approximately 1.67 times 10 to the negative 27 kilograms.
Compare that to neutronium, which is the highly dense material that makes up a neutron star. There's almost no space in between the neutrons and neutronium. So if we had neutronium occupying the same space as a hydrogen atom, it would contain a mass of approximately 8.37 times 10 to the negative 13 kilograms.
This is 100 trillion times heavier than that of a hydrogen atom. And if you just had 1 cubic centimeter of neutronium, it would in fact have a mass of about 1 billion tons. This would just fall straight to the center of the Earth.
Similarly to a figure skater tucking in her arms, a slow rotating massive star collapses to a radius of 10 to 20 kilometers, drastically increasing its speed of rotation. The combination of both collapsed magnetic fields and increased speed of rotation creates a magnetic field on the surface of the neutron star 1 trillion times greater than what we experience here on Earth.
And then in 1966, we believed to be receiving alien signals. But 2 years later, we determined that these were highly magnetized neutron stars called pulsars, creating beams of electromagnetic radiation from the north and south poles.
I know what we've told you so far about neutron stars makes them sound pretty scary, but trust me, that's just the tip of the iceberg.
There's a classification of neutron stars called magnetars, which are essentially pulsars with a magnetic B field 2 to 4 orders of magnitude greater than a pulsar.
And magnetars actually only emit highly intense beams of radiation in the form of X and gamma rays.
Magnetars are actually a fairly rare breed of neutron stars.
Only about 10% of neutron stars are actually born as magnetars. And as time goes on, these magnetars lose their vast speeds of rotation, decreasing their magnetic field, and then they just settle into pulsars.
However, pulsars can evolve into magnetars if they're close enough to a star that they start stripping away the star's material and absorb its energy.
The intense magnetic field strengths of magnetars bend and distort their crust.
Any small shift in the crust can cause starquakes, which are similar to earthquakes, but release immense amounts of energy.
In 2004, NASA scientists detected a starquake that released more energy in a fraction of a second than the Sun does in 150,000 years.
Some magnetars are classified as soft gamma repeaters, or SGRs, because they emit low-intensity gamma rays and high-intensity X-rays at irregular intervals, possibly due to these starquakes.
We can calculate the age of a neutron star with the following equation, where p is the period of its spin and p prime is its derivative with time.
The breaking index n is a natural factor that causes a decrease in the speed of an object's rotation. In a perfect vacuum, this factor is 3.
In 2007, the Crab pulsar had a period equal to 0.0331 seconds and a derivative equal to 4.22 times 10 to the minus 13 seconds per second.
Using these values, we can calculate a characteristic age for the 2007 pulsar of approximately only 1,240 years.
We hope you learned a lot about neutron stars today and how they're formed from massive stars.
Rotating at high speeds with intense magnetic fields.
Classified as magnetars or pulsars.
And when disturbed, give off violent starquakes. Thanks for watching.
Bye!
Nobody won that.